Hi everybody, and welcome to exercise 1 on our list of final exam review problems. And in this exercise we'll be talking about diagonalization of matrices. In this video in particular we're just going to be looking at matrix I here, the 2 by 2, seeing if we can do part A and B of this problem. Okay, so what is this asking us? Well, first they'd like us to find eigenvalues and eigenvectors and a basis for each eigenspace. Okay, so we'll do that, and we can answer that question. We can answer the question about diagonalizability in part B. Okay, so to find eigenvalues, we're going to start with the matrix A minus lambda I and look at its determinant. Okay, and this shouldn't be too bad because this is a 2 by 2, so let's just see what happens here when we take the determinant. Okay, do a little multiplying out here, and I'm going to skip a few steps and trust that you could do the algebra here. This simplifies down to lambda squared minus lambda minus 20, which then factors. Okay, so if we set that to 0, we can see that we're going to get two eigenvalues. It looks like 5 and negative 4 are the eigenvalues. So if we start with let's do 5 first. We're going to see if we can find the eigenvector or eigenvectors associated with that. So let's see, if we take 5 and substitute it into our A minus lambda I matrix, we're going to get negative 3, 3, 6, and negative 6. Okay, and I'm going to not write the 0, 0 on the right-hand side. Okay, just kind of reduce it as it is here. If we do a little row reducing to echelon form, we can get it down to this form, minus 1, 1, and then 0, 0. Okay, and you can look at that and see that we've got one pivot position up here. So we've got a free variable for x2, solve for x1, and we're going to get x1 equals t as well. Okay, and if we choose that free variable to be 1, we come up with an eigenvector that looks like 1, 1. Okay, associated with that eigenvalue of 5. Okay, same deal for x2. So if x2 is negative 4, and we do our substituting, this time we're going to get a matrix that looks like 6, 3, and 6, 3 again, it looks like. And if you row reduce that, okay, it's going to get down to that form. Okay, again, x2 is a free variable, so we'll let it be t, and that would mean that x1 is negative t over 2, it looks like. This time a convenient choice for t might be 2. Okay, and that's going to give us an eigenvector of negative 1 and 2. Okay, so let's see, what did they ask us for? We found eigenvalues, eigenvectors, and now we want a basis for each eigenspace. Okay, so we can maybe make a little table here. Okay, so for 5, we found one linearly independent eigenvector, so the set containing just our one eigenvector, that would be a basis for the eigenspace. And then for negative 4, basis for that eigenspace would be just negative 1 and 2. Okay, so we have completed part A of this, and part B is asking us, this matrix that we started with up here, is it a diagonalizable matrix? Okay, and if so, we want to write down those special matrices D and Q. Okay, well, how do we decide if something is diagonalizable? Remember that that's about having enough eigenvectors to form a basis, okay, for the entire space that we're talking about. And in this case, we've got our characteristic polynomial up in part A, so it's convenient to look at the powers. Notice that they're both 1 in the characteristic polynomial, and so one way to check for diagonalizability is to ask if the size of our eigenspace matches the multiplicity of our eigenvalue. Notice that for 5, we've got a basis that has one vector, And the same is true for -4. So since we got one vector for each eigenvalue, the multiplicity matches the size of our eigenspace. So the answer is yes, this is diagonalizable. Okay, we started with a 2 by 2 matrix and we got two linearly independent eigenvectors. And the only remaining thing to do then is to write down those matrices D and Q. Okay, remember D was just a matrix that had the eigenvalues down the main diagonal. Zeros everywhere else. Okay, and then Q was a matrix that had the eigenvectors as its column. We just want to be consistent with the order. So since we started with the eigenvalue of 5, we want the eigenvector that goes with it in the first column, 1, 1. And then for -4, -1, 2. And we're done.